Alright guys, this problem is the spinning disk problem. I'm just going to go through the variable of it. I'm not going to solve it. But we have a disk, and it has a radius, it has mass, and they didn't give us the angular acceleration. There's time. They gave us, it was from rest, the question. So it's from rest. So Wi is 0, and they gave us the final speed, the angular speed. Okay. Alright, so the first question. By the way, you can see the full question in the description, and I'm going to put the answer that I had before too. So what is the angular acceleration of the disk? So we're just going to use the equations. So we're going to use this one. W final equal Wi plus acceleration t. Okay. So this is 0 because start from rest. And then we have this one in question. And then we need to find this. So the equation will be W final over t. Okay. That's the answer. 2 is going to be, what is the angular displacement over the 18.5 seconds? Okay. So we can use the other equation. The final squared equal Wi squared plus 2 angular acceleration displacement. Okay, this is delta, but because we're assuming it start from like point 0, so delta 2 or delta final minus delta initial will be 0. So we're just taking delta final. So this one's also 0. W final squared equal to and then the angular acceleration, we got it from the question before. So theta will be equal the final squared divided by 2 angular acceleration. Cool. 3. What is the moment of inertia of the disk? This one you just have to memorize it, which is half the mass and then the radius squared. Okay. Number 4. So what is the change in rotational energy of the disk? Okay, so delta kinetic energy will be equal to kinetic energy final minus kinetic energy initial. Okay. So the kinetic energy is going to start from rest, so that means that the speed was 0, and then the kinetic energy of the disk at time equals 0 is going to be 0. So kinetic energy final, so it's half I W omega squared. Okay, and then you use the omega final on this. Okay, the one they gave us in the question before. And the inertia is the one we found in number 3. Okay. Number 5. Where is the tangential component of the acceleration of a point on the rim of the disk when the disk has accelerated to half its final angular speed? Okay, that's a nice question. So what we're going to do is the acceleration tangential is going to be equal to alpha r. Okay. So this is the equation for the acceleration tangential. So you use this guy from here, and use the r that they gave us. This is the radius. Okay. So number 6. What is the magnitude of the radial component? Radial component. Alright, cool. So we're going to use the equation that says radial, acceleration radial, is going to be equal to v squared over r. Okay, and this one is equal to, because v is equal to wr. And then when you square it, the ending product is going to be squared r. Okay, you use this guy. Use the half speed of it. Okay, so before you do this, so you omega divided by 2, the omega final divided by 2 before you plug it in here. Because it gives you in the question that's half the angular speed. Okay, remember. and then you get the angular acceleration, the radial acceleration. So number 7 is, what is the final speed of the point on the disk halfway between the center of the disk and the rim? Alright, so we have r nu, which is the one I drew in here. This is almost half of it, so we can use this radius in here. So v is equal to wr, omega r. So the omega doesn't change throughout the disk. All the particles has the same omega. So the only thing that changes is the radius and the v, the speed of it. And they're asking about the speed, they're not asking about the omega, because omega is the same throughout the whole disk. So you use the r nu. Let me call it small r actually. So r, small r, is equal to v equal omega small r. So use the r that they gave us in here. Okay, which is half of the big R. And then the omega is the same one as we had. Is it the 7? Yeah, the omega is the same one. Why am I thinking about it even? Alright, so number 8. What is the total distance, the point on the rim, did travel during the 18.5 seconds? Alright, so we're going to call it S, and then this is going to be equal R theta, which is the displacement. Okay, so the theta is the one you use from, what is it? The one from here. This is the one you use for the theta, and the R on the disk, so you use the big R, not the small r. Use the big R for it, and then you'll get your answer. Alright, hope this helped, guys. If you have any questions, just shoot me a text or shoot me a message, and then I'll get back to you as soon as possible.